Welcome back to the deep dive. Today we are strapping in for a bit of a journey under the hood of machine learning.
A deep one.
Yeah, a really deep one. We are moving beyond the sort of comfortable world of, simple linear models.
Right.
We're stepping into the complex, but I think really beautiful landscape of data structure,
Hmm.
how algorithms fundamentally perceive and really define groups and shapes within these massive data sets we're always talking about.
That's absolutely right. And our sources today are focused on two foundational concepts, but they're often misunderstood, I find.
How so?
Well, on one hand, we're looking at the strict, you might even say rigid, partitioning of data using k-means clustering.
Okay.
And then on the other, we explore this flexible, almost assumption-free art of non-parametric density estimation.
So they sound like complete opposites.
They do. They feel like they live on opposite ends of the modeling spectrum. But, and this is the key, they are mathematically intertwined in some really surprising ways.
Our mission for this deep dive, well, it's all drawn from the source material.
Right? F191 all the way to F229.
And we're not just scratching the surface here, are we? The
Yeah.
goal is a really rigorous, deep understanding.
No, absolutely not.
Yeah.
We want to trace the lineage of these common clustering methods,
Yeah.
find the single golden formula that, that really governs all density estimation.
And dissect that crucial difference. Is
Yeah.
it about fixing the size of your window
Yeah.
or fixing the number of points you look at?
Exactly. And this leads directly to the core insight we really want to deliver to you today.
The aha moment.
The aha moment. The thing that connects these seemingly separate ideas, the strict group assignment of k-means and the much softer probabilistic assignment of Gaussian mixture models, or GMMs.
Which we've talked about before.
We have. And we're going to show you the mathematical realization that k-means, this rigid tool that demands hard your in or your out assignments,
Yeah.
is actually just a special, extreme, and very constrained version of the much softer GMM.
Wow.
It's an elegant concept, and it reveals the hidden structural assumptions that are baked right into k-means from the very beginning.
Okay, that sounds like the perfect place to start. Let's unpack that relationship, starting with the stricter of the two cousins, k-means clustering.
Mm.
So, when we discussed the Gaussian mixture model previously, the key concept was all about soft decisions.
Mm.
And that felt really intuitive, didn't it? If an algorithm is analyzing a data point, it might say, okay, based on the probabilities, this point is, say, 80% likely to be in group A and 20% in group B.
It allows for nuance, for ambiguity,
Mm-hmm.
for points that are sitting on the fence between clusters.
Exactly.
Precisely. And F191 introduces k-means by defining its essential nature, which is that it's the polar opposite of GMM's nuanced approach.
No nuance here.
None. K-means demands all or nothing. A data point belongs wholly and entirely to one cluster, period. There's no probability, there's only assignment.
The ultimate goal here is pure partitioning. We're taking the entire data set, we'll call it X, and just slicing it up.
Slicing it into k non-overlapping fixed clusters.
And right away, we hit this massive practical constraint, which the source material brings up again and again. You have to decide on the number k beforehand.
Yeah, that's huge.
It is. This isn't something the algorithm figures out for itself. You, the human, have to tell it, I want 3 groups, or 5, or 10.
Just think about the implication of that for a second. If you are dealing with, I don't know, millions of customer records or astronomical observations, you have to decide, maybe kind of arbitrarily, whether the underlying structure has 4 major segments or 7.
You're making a huge assumption before you've even started.
You're committing to k before the algorithm has looked at a single data point, and that commitment fundamentally shapes the entire outcome.
So if you visualize the output, like in the illustration in F192, the result is just crisp. It's discrete.
K-means draws hard lines in the sand.
Right.
It literally partitions the geometric space. You look at a point and it's blue, or it's red.
No shades of purple.
No fuzzy boundaries, no transitional zones.
Yeah.
The absolute 1 out of k coding, the idea that a point is either in cluster 1 or cluster 2, that's the algorithm's defining characteristic.
But this simplicity, this sort of attractive crispness, it immediately leads us into some really tricky practical problems.
Pitfalls, yeah. F193 details them pretty clearly. The real-world ambiguities that these algorithms have to face.
And the first major one is just interpretation, especially with outliers.
Right.
So let's imagine a typical data set. You've got 2 large, pretty well-defined clusters, and then there's this one single lonely data point sitting way out in the middle of nowhere.
K-means has a duty to the k you gave it. If you said k equals 3, the algorithm is forced to make a judgment call.
What's the call?
Is that single point just an outlier, a piece of noise that we should, technically just group with its closest big neighbor?
Which seems like the sensible thing to do.
Or, because we mandated k equals 3, should the algorithm treat that isolated point as the prototype, the sole member of new cluster 3, and establish a center right there on top of it?
So the human researcher might see it as noise.
But the strict k-means algorithm is obligated to honor the input k. It has no choice.
And the second problem, which feels much more structural to me, relates to the shape assumptions.
Yes. K-means is mathematically engineered to prefer, well, round things, compact, spherical clusters.
But what if the data's true structure isn't round? What if it's two massive, long, elliptical clusters? Imagine two long, parallel cigars stretching across the space.
Well, because k-means is hunting for the most compact arrangement of points around a center, it might just completely ignore that elongated true structure.
And find what instead?
It could incorrectly partition those two long natural clusters into 4 smaller, rounder, but mathematically more efficient structures.
So it finds an answer that's optimal for its own rules, but totally misleading for the person analyzing the data.
Exactly. If you force k-means to find 4 round groups in a data set that actually has 2 oblong groups, the result will be mathematically optimal for k-means, but entirely wrong for you.
This is why the choice of K is often described less as a science and more as a highly informed art. It just influences everything.
It really does. It's a critical decision.
So if the algorithm is making these hard all-or-nothing assignments, how does it decide where the boundaries go? What's the mathematical engine driving this partitioning?
For that, we turn to F194, which defines the mathematical objective. We introduce the term IC, which is the cluster center.
The prototype.
The prototype, or more technically, the centroid.
And we're dealing with a kind of dual optimization problem here, right? We have two unknowns, and we're trying to solve for both at the same time.
Exactly. First, we need to assign every single data point, every xn, to the optimal cluster. And second, we need to position those cluster centers, the X, in the absolute best geometric location in space.
And best is defined how?
By minimizing the total sum of squared distances. Every point must be as close as humanly or algorithmically possible to its assigned center.
To formalize this, F195 introduces this indicator variable, ERINC.
Yes, and that's the technical term for the hard decision. ENC can only be a 0 or a 1.
Binary.
Binary. If rank is 1, it means point xn belongs to cluster K. And importantly, because of that strict partitioning rule, if you look at any single point xn, only one of its potential assignments, Rn1, Rn2, and so on, can be 1. All the rest have to be 0.
And the beauty of the cost function, which is called J, is how cleanly it captures this goal.
It's very elegant. J is defined as the sum over all the data points and all the clusters of that rank variable.
This 0 or 1.
Multiplied by the squared Euclidean distance between the point xn and the center x.
And that indicator variable, the rank, is what makes the calculation so efficient.
It's the switch. For any single point, only the distance to its one currently assigned center actually contributes to the total error J. We aren't wasting time and cycles calculating the distance to centers it doesn't belong to.
So the algorithm's entire purpose is just this relentless pursuit of minimizing this total sum of errors, J.
That's it. Make J as small as possible.
It seems like a very elegant objective function. You're guaranteed to be optimizing toward the tightest possible grouping, where, the variance within each group is minimized.
Right.
But wait a minute. If the goal is only minimizing squared distance, how does k-means handle, say, density differences? If we have two clusters and one is twice as dense but a little bit bigger, does the error function just automatically favor the denser, tighter group?
That's a really crucial insight. The square distance objective inherently favors groups that are compact and dense.
Because the error grows so fast.
Exactly. J increases rapidly if points are far from the mean. K-means doesn't really account for the number of points in a cluster in its error calculation beyond just summing up their individual errors. So it naturally gravitates towards solutions that minimize that variance.
A low variance cluster contributes less to the total error, J.
Right, than a cluster of the same size, but with high variance. However, you have to remember, K-means is entirely dependent on the spatial distribution. It only cares about geometric proximity, not statistical density in the way a GMM does with its probability components.
Okay, so we have this cost function, J, that we need to minimize, but we're kind of stuck.
A little bit.
We need to know the optimal assignments, the ranks, to find the optimal centers, the mix. But we need the centers to find the assignments.
It's the classic chicken and egg problem in optimization. F0196 calls it that directly.
So how do you solve it?
It's the reason why k-means, just like GMM, is fundamentally an iterative algorithm. We can't solve for everything at once in a single step.
So you break it down.
You break it down. You solve this by guessing a starting point and then alternating. You optimize one variable while holding the other one completely fixed. This iterative structure, though it's much simpler here, it mirrors the expectation maximization, or EM, algorithm framework.
So the process starts simply enough with step 1, initialization.
We just make a random guess for our K-cluster centers. These guesses are often pretty bad, sometimes even placing two centers right on top of each other or way outside any of the data, but it's a starting line.
And from there we go to step 2, the E step, the assignment phase.
Right, F197 covers this. In the assignment phase, we treat the current locations of the centers as if they are gospel. They're fixed. Our job now is just minimizing J with respect to the assignments.
This is the geometric part.
The purely geometric step. The action is really intuitive and, importantly, easy to parallelize. For every single data point, you calculate its squared distance to all k of the fixed centers.
And then?
The point is assigned to whichever center gives the absolute minimum distance. That specific rank is set to 1, and all the others are set to 0.
This is the part of the algorithm that makes the most immediate sense. It's like a global distribution problem.
How so?
If you have 1,000 delivery destinations and 5 fixed warehouses, the first optimization is just making sure every destination is assigned to the nearest possible warehouse. Minimize the total driving distance.
That's a perfect analogy.
So once those assignments are locked in, once we know exactly which points belong to which group, we move to step 3, the M step or the update phase.
Correct. That's an F198. Now the assignments, the ranks, are held fixed. Our goal flips. We now minimize J by moving the centers, the meeks, to the optimal position for their currently assigned points.
And this is where the choice of using squared distance really pays off mathematically.
It pays off beautifully. The math provides an extremely clean, what we call a closed-form solution. When you take the derivative of the cost function J with respect to a specific center and set it to 0, you're finding the exact position in space that minimizes the total squared error for that group of points.
And the result is?
The result is incredibly simple. Meek is just the geometric average of all the points currently assigned to cluster K.
You just move the center to the center of gravity of its cloud?
You literally shift it. You snap it right into the center of gravity of its assigned cloud of points.
Hence the name, k-means.
K-means. It iteratively calculates k-means. It's a beautifully simple, elegant, and computationally very fast solution compared to, say, the complex integral calculations you need in GMM's M step.
So we just keep doing that. E step, M step, E step, M step.
We continue repeating the E step, which is reassigning points, and the M step, which is recalculating the centers, until the process stabilizes, until it converges.
And convergence, as F199 notes, is defined as the point where no data point switches its cluster anymore during the E step.
Or when the change in that total error J falls below some really tiny predefined threshold.
And the guarantee here is important for the algorithm's stability. Convergence is always assured.
It has to be. Because the error function J is being strictly minimized in every single step, it can mathematically never increase, and because J can't be negative.
It's a sum of squared distances.
Right. The process has to eventually settle down. It has to stop somewhere.
However, there's always a however.
There is. The critical caveat, the elephant in the room for k-means, is that convergence is only guaranteed to a local minimum.
Not the best possible answer.
Not necessarily. If your initial random starting centers were chosen poorly, say they fell into some weird tight configuration that wasn't representative of the global structure, the algorithm might rapidly find a suboptimal solution. It finds a little valley in the error landscape and just gets trapped there.
So it achieves stability, but the final error J is much higher than the absolute minimum possible error.
Correct.
So if the solution depends so heavily on that initial random guess, how do practitioners actually handle this? I mean, you can't just run it once and hope for the best.
You can't. As detailed in F199, the practical solution is, well, it's brute force.
You just run it a bunch of times.
A bunch of times. You run k-means multiple times. A typical industry standard might be 10, 50, even 100 times, and each run starts with a completely fresh set of random initial center.
And then you just pick the winner.
You pick the winner. Once all the runs are complete, you simply choose the result, the set of clusters that gave you the lowest final total error J.
Yeah.
If you found the deepest valley after 100 tries, you just had to assume that that valley is sufficiently close to the true global minimum.
That makes perfect sense. You mitigate the risk of a bad start by having a lot of starts, and we can see this process play out in the demonstration from F200 through F202.
We can. You start in F200 with a high error state based on some arbitrary initial placements.
Then the first E-step in F201 instantly creates these harsh straight-line boundaries. It's just simple proximity.
And then the M step on the right in F201 shows the centers leaping dramatically. They move toward the actual center of gravity of their assigned points, and that results in a massive, immediate drop in error.
And the error curve in F202 confirms this whole dynamic. There's a huge, almost vertical initial plummet in J as the centers just rapidly move into the general neighborhood of the data clouds.
And after that, the curve flattens out. That indicates only minor adjustments are happening, the fine-tuning, until it becomes perfectly flat and converges, maybe within 50 iterations in this example.
Right.
It confirms that the local minimum has been reached and no further movement will decrease the cost J.
Okay, this brings us to what you teased at the beginning, the really big mathematical insight.
Yes. Now we arrive at the most compelling theoretical point of this section. It's detailed in F203 and F204. And this insight, it really fundamentally reframes k-means.
That it's not some entirely different algorithm from GMM.
It's just a mathematical limiting case.
Okay, so we have the soft probabilistic GMM and the hard absolute k-means. How do you get from one to the other? What constraints do you have to put on GMM to force it to behave like k-means?
We impose two very severe restrictions on the GMM structure.
Oh.
First, we remove any a priori preference for one cluster over another. We do that by mandating that the mixing weights, the picks, are all equal. Every cluster is assumed to be equally important.
Okay, that's one.
Second, and this is the mathematical key, we force the covariance matrices, the sigmax, to be spherical perfect balls and identical for every single cluster.
Spherical and identical, so every single Gaussian bell is the same size and perfectly round.
Exactly. We represent that constraint by setting the covariance matrix sigmac equal to epsilon times I, where I is the identity matrix, and epsilon represents some tiny fixed variance value.
And the smallness of epsilon is the crucial part.
It's everything.
So if I'm connecting the dots here, that spherical assumption is what fundamentally limits k-means' ability to find those long, cigar-shaped clusters we talked about.
Precisely. It's baked into the math before the process even starts. K-means inherently assumes circularity because the covariance structure that mathematically transforms GMM into k-means is defined as spherical.
Okay.
Now, when you substitute these constraints into GML's complex formula for calculating the responsibility, that soft probability measure, the formula simplifies a lot. It still has an exponential function of the negative square distance between the point and the center.
But now that distance is divided by that tiny variance, epsilon.
Yes. And here's where it gets really interesting. What happens when we take that variance, epsilon, and we let it approach 0? This is the limiting operation described in F204.
So as epsilon gets smaller and smaller.
As epsilon approaches 0, the denominator of that exponent shrinks towards 0. And what that does is it makes the Gaussian bells become infinitesimally narrow and impossibly tall.
Okay.
Mathematically, that exponential term acts like a severe gatekeeper. When epsilon is tiny, any difference in the numerator, even a minute difference in the distance, gets amplified dramatically in the negative exponent.
This means if two centers are almost the same distance from a point, the one that's even a tiny bit closer just dominates.
Overwhelmingly. The term corresponding to the center with the smallest distance instantly becomes orders of magnitude larger than all the other terms. The soft probability calculation completely collapses.
So the probability for the nearest one goes to 1 and the others go to 0.
Exactly. The responsibility for the nearest cluster approaches 1, and for all others, it approaches 0. The nuanced, soft GMM decision has mathematically transformed into the hard, absolute k-means assignment.
Wow.
And this rigorous realization confirms that k-means is inherently biased toward finding spherical compact clusters because it is the zero variance limit of a model that is built on spherical assumptions.
That wraps up our dive into the rigid world of k-means. We were optimizing toward a defined shape spheres and a defined number of groups, k. Now let's step into a completely different philosophical space, non-parametric density estimation.
For the last several deep dives, we've really existed in the world of parametric models, GMM, k-means, even the basic Gaussian distribution.
And the approach there is always to make a strong assumption first.
Right. You say, I assume the data follows this specific known mathematical formula, which is defined by a small set of parameters, like the means and the covariances.
And that approach is really efficient. You only need to store a handful of numbers, even if your dataset has billions of points.
It is. But F205 summarizes the critical downside. If your underlying structural assumption is wrong, if the data doesn't actually fit a bell curve or a collection of them, the model fails.
And not just fails a little bit, it fails spectacularly.
Right. If your data forms some complex structure, a spiral, a horseshoe, or maybe a set of points that looks like a constellation, trying to force a Gaussian bell curve onto that it's worse than useless.
Why worse?
Because the resulting model will be actively misleading and inaccurate. It's trying to fit a geometric square peg into a spiral hole.
So non-parametric density estimation just throws away the template.
Throws it right out. We make no rigid assumption of shape. We just let the data speak for itself. We want the structure to emerge organically from the data, governed only by the proximity of the points themselves.
So we're trying to estimate the probability density function, fx, without defining its mathematical form beforehand.
And the most rudimentary tool for this, the intellectual ancestor of all these non-parametric methods, is something everyone is familiar with.
The histogram.
The humble histogram.
Okay, the histogram, F206, is simple. We divide the data range into bins, or classes, each having a fixed width, which we call delta.
And we count how many observations, ni, fall into each bin. But, and this is a common mistake, we have to be careful not to confuse a simple count with a true probability density function.
Right, because for a function to be a proper probability density, the total area under the curve has to integrate to exactly 1.
To achieve this normalization, we have to perform a crucial step. We divide the count in the bin, ni, by the total number of observations, n. That gives us a relative frequency. But then we also have to divide by the bin width, delta.
So the height of the bar, phi, is the actual density estimate. It's the assumed constant density within that one bin.
It's the mass, which is ni over n, spread over the width, or the volume, which is delta.
But this simplicity immediately traps us in what the source material calls the delta dilemma.
Yes, F207 and F208 analyze this. The choice of delta, the smoothing parameter, is absolutely paramount. And finding the right delta is incredibly challenging.
Let's take the first case. If delta is chosen to be very, very small,
You get the top image in F207. The resulting density estimate becomes incredibly jagged and noisy.
where 2 points just happen to have clumped together, you get a huge, isolated spike.
And where there was a slight gap, the density just drops to 0. You're modeling the noise and the random fluctuations of your specific sample, not the underlying true distribution. This is undersmoothing or overfitting.
The variance of our estimate is extremely high.
Right. On the opposite extreme, if delta is chosen to be very large,
That's the bottom image.
right, the density estimate becomes oversmoothed. F208 confirms that all the interesting structural detail is just lost. If the true distribution is bimodal, if it has 2 distinct peaks, a large delta will just force those peaks to smear together into one single broad amorphous block.
That's underfitting. You've introduced high bias by just averaging away the critical underlying structure.
So we have this tightrope walk. A small delta gives us too much noise, so high variance, and a large delta smooths away the real signal, so high bias.
It's the classic bias-variance trade-off in its purest form.
And histograms are computationally fast. They're great for simple 1- or 2-dimensional visualizations. And once you've calculated it, you can actually discard the raw data, which is a nice feature.
Right.
But F210 lays out the 2 fatal flaws that make the histogram a non-starter for serious high-dimensional machine learning.
The first flaw is the unnatural discontinuity. The density function just jumps abruptly at the bin boundaries.
Which we know intuitively that most natural processes don't work like that. They change smoothly. A density estimate should flow, not leap.
But the second flaw is the real killer.
It is the curse of dimensionality. This is the catastrophic lack of scalability in high-dimensional space.
So if we try to use a histogram in a space with many features, say 10 dimensions, which is actually a pretty small number in modern big data problems, the number of required bins just explodes exponentially.
Let's break down that explosion. If we use a very modest 10 bins along each dimension.
Which is already pretty coarse.
Very coarse resolution. A 1-dimensional space needs 10 bins. A 2D space needs 10 times 10, so 100 bins. A 5D space needs 10 to the power of 5, or 100,000 bins.
Okay, but a 10-dimensional space.
Requires 10 to the power of 10. That's 10 billion separate hyperboxes.
10 billion.
10 billion. And even if your dataset N is massive, say you have 1 billion points, most of those 10 billion hyperboxes will remain completely empty. The data becomes incredibly sparse.
And if a box is empty, its density estimate is 0, which is probably wrong. If it has 1 or 2 random points, its estimate is extremely noisy.
And the model requires massive memory just to store all those empty boxes. The resulting density estimates are rendered totally meaningless by the sparsity and the high variance.
So this failure to scale forces us to just abandon the rigid, fixed grid of the histogram.
We have to. We need methods that adapt dynamically to where the data actually lives. We need to focus our estimation effort only on the local neighborhoods where points actually exist, and that's how we bypass the tyranny of the empty hyperbox.
Okay, so F211 helps us synthesize those failures into 2 governing principles for any good non-parametric model.
Right. First, locality is everything. To know the density at some point x, we must look only at its immediate neighborhood, usually defined by Euclidean distance.
And second, the lesson from that delta dilemma.
Yep.
A smoothing parameter is absolutely critical. We need some kind of regulator to balance high variance or noise against high bias or structure loss.
These 2 principles are the bedrock for the 2 champions of non-parametric density estimation. They're introduced in F212. Kernel density estimation, or KDE, and K-nearest neighbors, or KNN.
But before we get into the differences, we need to derive the single unifying mathematical concept that governs how all of this works.
The master formula, as the source calls it, how all density estimation works when you look locally.
So we start with pure analysis in F213. If we have some unknown density function, fx, and we define a tiny region, r, around a specific point, x,
Then the probability, p, that a randomly drawn point lands in that region, r, is approximately the density at x fx, multiplied by the volume v of that region.
and this assumes that because the region is so tiny, the density is basically constant within it. So p is about fx times v.
Right. Now we bring in statistical observation. This is F214. We look at our total data set, n. If we observe k points falling into that tiny region r, then the fraction k divided by n is our best statistical estimate for the true probability p.
And as our data set n gets really large, this empirical estimate k over n becomes highly reliable. Its variance shrinks.
So p is also about k over n.
And F215 is the satisfying moment of synthesis. We just set the calculus approximation equal to the statistical approximation.
So fx times v is approximately k over n. We just rearrange this equation to solve for the density function we're looking for, fx.
And the resulting master formula is fx is approximately k divided by n times v.
That is such an elegant, concise concept.
It really is. Density is simply the mass, the observed fraction of points, k over n spread over the volume v in which they were found.
If you find a fixed mass compressed into a tiny volume, the density must be high. If that same mass is spread across a massive volume, the density is low. This core physical intuition, mass divided by volume, is the mathematical basis for all these modern methods.
But while the master formula is elegant, it conceals a huge practical challenge.
A massive one. F216 details this fundamental contradiction in the requirements. For mathematical precision, we need the region R, and thus the volume V, to be infinitesimally small, so that density really is constant within it.
But for statistical stability, to avoid that high variance, we need V to be large enough to make sure a statistically significant number of points, k, actually fall inside.
If k is too small, like if k is just 1, our estimate k over n is highly volatile and noisy.
So we have to find that sweet spot, a compromise where V is small enough for the local assumption hold, but large enough for the point count k to give us a stable, reliable estimate.
And this inherent dilemma forces us into the 2 primary opposing strategies. They're outlined in F217. Both strategies manage this trade-off by fixing one variable, either k or v, and allowing the other to be determined by the data.
Strategy 1 is the k-nearest neighbors, or KNN, approach.
We fix the count k, we decide I must have exactly 10 neighbors. Then we let the volume v float. We dynamically expand our search space until we capture exactly those k neighbors.
And strategy 2 is the kernel density estimation, or KDE, approach.
We fix the volume v. We decide I want to look inside a specific fixed-size hypercube. Then we let the count k float. We just count how many points happen to fall into that predetermined fixed volume.
Let's dive into the fixed volume approach first. That's KDE.
So in KDE, we define our volume v using a bandwidth parameter, h. If we're using a simple hypercube in g dimensions, the volume is fixed as v equals h to the power of d.
And F218 introduces the mathematical tool we use to count the points inside this fixed volume. It's called the kernel function, KU.
Initially, mathematicians often used a very rigid kernel, which is known as the Parsons window. This kernel function basically acts like a simple switch.
On or off.
On or off. It returns 1 if a point is inside the fixed hypercube of size h centered at x, and 0 if it's outside. It's just a geometric inclusion test.
So F219 shows how this fits back into our master formula. The total count k is estimated by summing up the contribution of this kernel function for every single data point.
And we insert this estimation of k back in the formula fx is approximately k over n times v, where v is h to the d. The resulting density estimate is influenced by every point, weighted by that kernel, and normalized by that 1 over n times h to the d term.
The visual interpretation in F220 is really essential here. The way the formula is structured means that for every single data point in our data set, we are mathematically placing a rigid block, a hypercube of a certain height, onto it.
A height of 1 over h to the d, centered at that point xn. The overall density function fx is just the summation of all these rigid blocks stacked on top of each other.
And that visualization instantly flags the issue we were trying to escape from with the histogram: discontinuity.
Right. Stacking rigid blocks means the resulting density function is a stair-step function. It has hard edges and abrupt jumps. It's the same problem, just now the bins are centered on every data point instead of on a rigid global grid. It's unnatural.
So if we want a smooth, flowing density curve, we have to replace the rigid parsum box with a soft, smooth kernel function.
This is the shift that's described in F221. We replace the hard box with a continuous function, most commonly the Gaussian kernel.
So instead of placing a rigid block on every data point,
We place a small, soft Gaussian bell, or a hump. The center of this bell is the data point, and its width, or its standard deviation, is controlled by our critical parameter, h.
the resulting density, Fx, is therefore the sum of n of these smooth, tiny Gaussian bells. And because you're summing continuous functions, the final result is a beautifully smooth, continuous density estimate that avoids all those abrupt jumps.
And now, h, which we call the bandwidth, becomes the ultimate smoothing parameter. It's in F222. It plays the same critical role as the bin width delta did in the histogram. It determines the bias variance trade-off.
Let's examine the extremes of h. If the bandwidth is tiny, say 0.005, like in the top illustration,
Then every data point generates an extremely narrow, tall needle spike. The Gaussian bells are so localized and narrow, they barely even overlap.
the density estimate is just dominated by these isolated spikes.
You are massively overfitting. You've essentially just memorized the exact locations of the individual data points, but you failed to generalize the underlying structure. This gives you extremely high variance.
On the other hand, if h is large, like 0.2 in the bottom illustration,
The Gaussian bells are so broad and shallow that they completely merge and flow into one another. Everything just gets smeared out into one single massive hill.
any true structural detail, like the clear bimodality of the underlying distribution, is completely obscured.
This is extreme underfitting, or high bias. We've averaged away the signal.
So the magic is finding that medium h, like the 0.07 in the middle example.
At that sweet spot, the individual bells merge nicely, they smooth away the localized noise, but they still clearly reveal the true underlying structure. F223 really drives home the point. The entire art of KDE is achieving that optimal balance.
And since there's no formula for the mathematically perfect h,
It is almost always chosen empirically, often using rigorous methods like cross-validation to test which age generalizes best to new, unseen data.
so let's summarize the final assessment of KDE.
Well, F224 provides the basic requirements for any function to be used as a kernel. It has to be normalized, so its integral is 1, and it has to be symmetric.
Okay. And the pros and cons are in F225. The primary advantage is something called lazy learning.
Right. You don't have to train a complex iterative algorithm. There are no E steps or M steps. The data is the model. When you want a density estimate, you just run the calculation based on the existing points.
But the disadvantages are substantial, and they limit its application in the modern age of truly big data.
The first issue is memory. You have to store all n data points in memory to make any calculation. If n is in the hundreds of millions or billions, this becomes untenable, especially compared to a model like GMM, which only stores a few parameters regardless of n.
And the second major drawback is computational time. Every single time you want to query the density at a new point x, you have to calculate the distance and the contribution of all n existing data points.
If you have 10 million data points, that's 10 million distance calculations for one single query. This makes real-time applications incredibly slow.
And finally, there's that inflexibility constraint we noted. The bandwidth h is constant across the entire space.
Which is a severe limitation.
Yeah.
As we said, if data is very dense in one region, You desperately want a small h for high precision and low bias. But if the data is sparse in another region, you need a large h to capture enough points for statistical stability and minimize variance.
And standard KDE can't do that. It can't adapt locally.
It can't. And this limitation leads us directly to the solution proposed by KNN.
If KDE's fixed bandwidth is such a liability, it sounds like we need a method that automatically adjusts its search radius based on local density, right?
Exactly.
That brings us to KNN.
So we fundamentally flip the strategy used in KDE. In K-nearest neighbors density estimation, F226, we fix the count K, and we allow the volume V to become the variable that the algorithm determines.
And the principle is beautifully intuitive. It immediately solves KDE's inflexibility problem.
It does. We set our constant, K, let's say K equals 10, and we stand at the point X where we want to estimate the density.
Then we just inflate a sphere around that point.
You inflate a hypersphere, expanding it just until you've successfully captured exactly K data points. The radius of that sphere then defines the required volume V.
And the implications of that are huge. If you're standing in a region where points are tightly packed, you only need a tiny sphere, a small volume V, to find your K neighbors.
But if you are standing in a sparse, empty region of space, you have to inflate a massive sphere, a large volume V, to find the same K neighbors.
And because our master formula dictates that density, Fx, is proportional to 1 over V.
Since K and N are now fixed constants.
The relationship is perfectly inverse. Small volume V automatically means high density, and large volume V automatically means low density.
This is the critical advantage of K and N density estimation. The smoothing parameter, which is now the search radius, is not fixed globally. It adapts dynamically to the local density of the data.
So where the data is dense, the function becomes narrow and peaked. And where the data is sparse, the function is automatically broad and smooth.
Exactly.
So now the smoothing regulator is K, the fixed count of neighbors we demand. What happens when we change K?
F227 gives us the visual evidence, and it shows the same fundamental bias variance trade-off we saw with the histogram and with KDE.
So if K is chosen to be very small, say K equals 1.
That's the top image. We look only for the single nearest neighbor. The resulting volume V required to find that lone neighbor is usually infinitesimally small.
And since density is proportional to 1 over V,
this leads to huge, noisy density spikes right at the location of every single data point. The estimate is extremely unstable. This is severe overfitting and very high variance.
Conversely, if K is chosen to be very large, say K equals 30 in the bottom image,
we demand a massive neighborhood to find all 30 points. The resulting volumes V are enormous, and the density estimate becomes wide and smoothly averaged across these large regions.
You lose the fine structural details. You smear away complex shapes like the bimodality,
which is classic underfitting and high bias.
Yeah.
F228 emphasizes that familiar dilemma. The choice of K is paramount. Too small, and we model noise. Too large, and we lose essential structure.
You need that middle ground K.
That balances the statistical need for stability, which is low variance, with the mathematical need for localization, which is low bias.
It sounds like computationally, KNN is doing a bit more work up front to find that required volume V.
It is.
But it gains this critical adaptability that KDE lacks, which makes it a stronger contender in real-world scenarios where data density varies a lot.
That's precisely right. It costs more initially because finding the K nearest points is a complex search problem. But the resulting density map is far more representative of the data's true, complex underlying structure than a map that's constrained by a fixed bandwidth H.
Okay, so let's get to the critical assessment of KNN.
Right. F229 wraps up our density estimation discussion with a critical look. Despite its intuitive power and that local adaptability, it has one major theoretical flaw that often bothers purist mathematicians.
Which is?
The resulting function is not a true density function because its integral over all of space diverges.
Diverges? What does that mean practically for a data scientist?
It means that if you try to integrate the estimated density fx over the entire infinite space, it does not sum to 1, or even a finite number.
Why not?
As you move extremely far away from the data cloud, the required volume V to find K neighbors grows infinitely large, but the density estimate, which is proportional to 1 over V, it doesn't approach 0 fast enough.
So in the empty, far reaches of the space, the estimate stays non-zero for too long.
Exactly. Now, for practical applications that are focused on the data cloud itself, this theoretical flaw is usually irrelevant. The structure within the data space is what really matters, and KNN captures that structure beautifully.
But just like KDE, it suffers from that storage constraint.
The model is the data. plus your choice of K. You have to store the entire dataset, which limits its practical use in these massive big data scenarios where memory is a bottleneck and you have to make a lot of queries.
But still,
But still, the simplicity of the underlying K&N principle, relying purely on proximity and the consensus of neighbors, is profoundly powerful.
and that realization, using neighborhood consensus to make fundamental decisions.
Is the intellectual springboard that leads directly to the widely used K-nearest neighbors classifier. It transitions the concept from abstract density mapping to concrete decision-making.
That's a fascinating pivot point. We've used K to define where the density lives, and now we're prepared to see how that same K can define what class an object belongs to. This deep dive has been a comprehensive journey through how these algorithms perceive structure. It's been fascinating.
Covers a lot of ground.
We started in the strict, constrained world of k-means, clustering, the rigid, zero-variance limit of the probabilistic Gaussian mixture model.
And that mathematical realization really confirms why K-means is only truly effective when it's dealing with perfectly spherical, compact data structures.
We then explored the necessity of non-parametric methods, driven by the catastrophic failure of the histogram when it faces the curse of dimensionality.
Showing why the vast emptiness of high-dimensional space just renders those fixed grid methods totally unusable.
We discovered the single, unifying conceptual key to all of this, the master formula. Density is simply the count of neighbors K over the total observations N, scaled on the volume V required to contain them.
Density equals mass over volume.
And we learned that the entire field really splits based on which variable you choose to control.
Yeah.
Do you fix the volume, V, with a bandwidth, and let K float?
Which is kernel density estimation, stacking those smooth Gaussian bells.
Or do you fix the count K and let the volume V float?
Which is K nearest neighbors, allowing the estimation to adapt dynamically to local density. And the choice is always a careful trade-off between bias and variance, between smoothing out noise and losing essential structure.
You now have the full toolkit for analyzing data distributions. Whether you're trying to partition data into hard groups with defined boundaries, or estimate its flexible, continuous underlying shape without making any prior assumptions.
And here's the final provocative thought to consider as we wrap up. We use the K-nearest neighbors principle to estimate density, an abstract, continuous metric based on proximity.
Right.
If this robust principle works so well for understanding spatial distribution, how much more powerful is it when we apply it to a classification problem?
So instead of calculating the volume V,
What if we simply identify those K nearest neighbors and just immediately ask them, which class are you? The consensus of proximity, moving from abstract density measurement to concrete, actionable classification decisions. That is perhaps the ultimate power of neighborhood methods in machine learning.